So in the last class, we talked about the beginning of electromagnetic radiation and some characteristics of light. We're going to specifically now talk about a lot to do with reflection and how light can be altered. Whether the color is altered, whether the angle that it's traveling at is altered, whether the EM wave and the EM wave is rotated to change what's called polarization. So we're going to talk about things that affect light today. We'll start first with the term, and this term is something you know, obviously. You look in the mirror all the time and you see your reflection. So when the EM wave is redirected, and this doesn't necessarily mean right back at you. So for example, if you think about like the large, what look like satellite dishes, they're really antennas that are placed at certain locations to boost cell phone signals for Verizon or whatever it may be. You have antenna towers also. But I'm talking about the ones that are like bowl-shaped with a little sensor in the middle. So it's very important that we understand how reflection works, because reflection enables us to have things like this antenna that receives a signal that gets redirected toward the center. Okay, now we can talk about simple surfaces like mirrors where it's reflected toward you, the light that you're seeing. But the applications of this are what are really important. Okay, so we're going to talk about reflection, but think about examples where EM waves need to be reflected in order to serve a purpose. So let's talk about two. They're pretty self-explanatory. The diagram alone probably shows you exactly what it is. Look at the diagram. We're going to see that we have diffuse and specular. What do you think they are, basically? You can read, obviously, but just based on the diagram, what do you think happens here? What's going on physically? Ellie?
Well, the light, I guess, is like reflected off the diffusion, and it kind of goes all over the place because the surface is flat.
Good. And then?
And then that one is, since it's flat, it has a direct angle.
Yeah, I mean, if I were thinking about this, I would think of part B as like if I were playing pool. Right? Ask Mr. Hall. If I were playing pool, hit the ball into the bumper, it'll come off the angle that I hit it. That's how a lot of people calculate. That's why you ever see at a pool table, there's those dots along the length of the table. Those dots are to give you markings of length. So that based on the length, the way you are in this direction, and the length you are here, you could actually calculate the angle every time. You use inverse tangent, or inverse sine, inverse cosine. So anyway, the idea here, a smooth surface, it is reflected at the same angle which it hit. But a specular surface, but a diffuse surface where it's really rough, we're going to see that the light rays come off at some random angle. Now, what do you think are examples of this? What would be an example of a diffuse surface where you wouldn't get much reflection off the surface, at least reflection that would be coming at the same angle to affect you? What would be a surface that's diffuse?
So like when you throw a pebble on the pond and the water is like already wavy, and so...
If the water were already wavy.
Yeah.
Agreed. Okay? Because the water itself would be the surface. What else? What would be diffuse? Think about surfaces that have that kind of contour.
I know the other one.
The other one we'll get to. Yeah, mountains or the ground, the earth maybe. The earth is a great example. If you're walking through like a park or a trail and you have the dirt would look like this, right? Is there much reflection off of dirt, like light reflection? No, there's not much. These rays get scattered. They don't reflect off perfectly like you would in a specular surface.
I was thinking mountains, but with snow.
Yeah, any snow-covered surface, great example. How many people have gone skiing before and gotten sunburned really bad? You're like, it's not even sunny out today. Why is it?
It's a goggle tag.
Yeah. That snow reflects the light, so you're getting the light from the sun, and this light that's not hitting you from the sun gets reflected off the snow. A lot of guys you'll see come back with like a beard, like burn almost sometimes, and it's usually under here, because the light is being reflected from the snow. You don't get much of this light, especially because you're wearing goggles too, or a hat or something.
I think those things where you tan with things.
Yeah, we used to tan on rooftops. So my mom grew up in Italy and then moved to Brooklyn when she was like 15, her family. And they used to sit on the roof of the house. I actually live in this house now. They used to sit on the roof in the summertime, and they would put like, I guess oil, tanning oil, and they would set up like metallic sheets around them to literally magnify the rays to get a better tan.
That's good.
It's so unhealthy, and like she would never do it now, obviously. But 40 years ago, I was like, oh yeah, do whatever you can to stay tan. Not thinking about UV rays and stuff, you know. But yeah, they used to literally set up those metal. You know what they would do? How would they make them? They would take a cardboard box and put tinfoil. That's what they would do. Wrap it around the bottom, tape it on. They would set up these like cardboard lined boxes. But yeah, good example of specular surface. Okay, so two types of surfaces that we're going to look at now. If we do surface, if we do, this is what we'll see. And we can see it clearly with the flashlight here on the left, but to show it specifically, we'll see that the angle, what we call of incidence, the angle of incidence, theta, is equal to the angle of reflection, theta prime. The little apostrophe means prime. Okay, right here. But these angles are equivalent. Theta equals theta prime. The angle coming in equals the angle going out. All you got to remember, think of pool, like billiards, pool. Okay, the angle that you hit the ball at when it hits the bumper, it comes off at that angle. Assuming the ball is not spinning. It can rotate, which is fine. But if it's spinning, sway it off, somebody hits the side of the ball to spin it to cause it to rotate, it'll come off differently. But if you hit it directly and it comes off, this is what it would look like. I'm trying to think of another example of that. I don't know. There was an old video game, was it called Pong? Where the ball would be hit back and forth on Atari, and the ball would go back and forth. It followed these laws for sure. The angle it hit at would be the angle it came off at. I don't know, think of other examples. Okay, so the angle of incidence and reflection are always going to be the same. We're going to take this idea and expand upon it more in chapter 15 when we talk about surfaces that are not necessarily going to reflect, but they're going to pass the light through, like a window pane. That's called refraction. Okay, but we're going to look at reflection here. And we're not going to get to the next section until after the next test. So this test is going to be mainly on chapters 12 and 14, ending at 14. We'll start 15 up after the test, which is also related to light, but in a different aspect of not just reflection, but refraction. So let's quickly take a look at this idea of the visible spectrum. You know this. Some of you alluded to it the other day. Somebody even said, where's your bib? Indigo is not included in the diagram. It doesn't really matter. Okay, it's between blue and violet. The spectrum has to do with the frequency. So if you remember, you had a table yesterday. And in that table, we went from different frequencies, going from high to low or low to high, going from one end, which was like gamma, all the way to the other end, which was radio. Radio with the longest frequency, longest wavelength. So they had the shortest frequency or the smallest frequency. Well, if you remember, the visible spectrum was that little bandwidth in the middle. The different colors you see have to do with the frequency of the EM wave that's actually meeting your eye. So for example, when you're seeing red, you're seeing a specific frequency of light. Now, if I shut off all the lights in the room, you can still kind of see color because there's some ambient light in there, right? But if you literally covered all the windows, covered the door, shut the light, do you see anything? What do you see? Yeah, you see the absence of light, right? You see the absence of light. Oops. You see the absence of light itself. So what you're seeing is the color that's actually being reflected to you. So when you see your tie is red or a shirt is yellow or your shirt is green, that means that that color is being reflected toward you and that the material is absorbing all the other colors. Okay? You're seeing what's being reflected toward you. So when you don't see anything, it means all the colors are being absorbed or there's literally no light. So like this desktop right here is the absorption of all the colors of the spectrum. That's what the color black is. The color white. Anybody know what the color white is?
Isn't that a reflection of all light?
It's the reflection of all the light, of the colors of light. So white light meaning, all the colors together. That's what you're seeing when you see like a piece of paper. All the colors are being reflected toward your eye. Okay, so if I were in the summer and I was going to the beach, what color should I wear?
Black.
Yeah, on the beach?
If you want a tan.
But you'd have a shirt on.
So you want to be real hot.
Oh, then you're gonna be really hot, but I really like swimsuits and shirts.
But if you don't want to be hot at the beach,
Well, you didn't specify.
sorry,
Like a white tank top.
if you want to go to the beach and really sweat, wear black.
Black.
All right, but if you want to go to the beach and you want to wear a shirt and you're not tanning, a white shirt would reflect all the colors better. And you'll feel that in the summer. Frank, what was your example?
I said a white tank top.
A white tank top.
Oh,
Okay.
perfect summer outfit.
How many people in the summer have played basketball on a driveway or a blacktop? Have you ever done it barefoot?
Yeah, it
It's
hurts.
ridiculous.
It hurts so
It's
much.
hot.
Oh,
It's so hot. In my backyard when I was a kid, we used to rent part of our house, so it was like an apartment. So there was a driveway in the backyard. And when we stopped renting, when me and my brothers were born, my dad made it into a basketball court. He painted it all, put a hoop up and stuff. So we had like a little driveway, but it was a blacktop. So in the summer, we had a pool actually. We were lucky enough that we lived in the suburbs. So we would actually take the hose. In the beginning, we would take the water out of the pool until my dad yelled at us. But we would spray down. Within like 10 minutes, it would absorb all the heat and it would heat up right again. So it really didn't matter because of the color. It absorbs all the colors of the spectrum.
there's so many
It's
black
kids.
leather seats there.
Oh,
Oh, that's always.
black leather in the summer is the worst feeling ever.
No,
Get in
the
and-
safety belt.
You can't
And you're
even
like
hold the
scared.
seatbelt.
No, it's gonna hurt.
And the buckle on the seatbelt would like,
So
you would brand yourself. You would like go to put it on, you're like, oh, it just singed my skin. It's like burnt. Yeah. Let me see if there's anything else I wanted to say about this. No. Let's take a look at the primary colors of light. Now, let me preface with of light. I'm not talking because I know there's artists in the room. These are not the three primary colors you use to mix. What are the three primary? Who's in art? Who's in art? Who knows the art?
I don't.
What are the three primary colors in art that you mix?
Red, blue, yellow.
Someone's been paying attention.
Is it red, blue, and yellow?
Yeah.
All right. So I guess green takes the place of yellow for light. I'm not sure how this works exactly with colors, with paint. I know it works with light. So here's what's happening. The color red up here, the color blue, and the color green all together will make white light. If you had three filters on top of one another. And you can actually try this. If you get cellophane, you know what cellophane is or no? You wrap like 6 Foot Heroes in cellophane. It's like this translucent red material or blue or yellow, whatever. If you use cellophane, you can actually prove this true. So if you wanted to make yellow, you can take green and red cellophane, lay them over each other, and shine a light through it, yellow light will come out the bottom. Okay, you can literally just take, they're called filters really. You can buy a set of these for like a science kit. I didn't do it honestly because it's kind of trivial, or you could do it very simply on your own. So if you want to do it for extra credit, and you could actually prove it, by all means, let's do this. Let's make this one of those. So here's where your extra credit would be. Get some sort of light filter. Cellophane is a good example, but you don't know those primary colors, so a shade of it might not work very well. But if you could even get like one of these, like any store, you can get like a little science kit that has all different color filters, and you could lay them next to each other, shine a flashlight through, and see the color that comes out the other end. You probably have to do it in some sort of darkness, not necessarily all dark, but the room needs to be pretty dark. Shine a flashlight through the filters, see the combination of two filters giving a third color. Is that clear? Okay, so not just like a blue sheet of cellophane with a light through it, because all you're going to see is blue light come out. You could start with that, but then I want you to put some colors together to come up with others. Okay? Now, some interesting stuff about the primary colors. How many people are interested in electronics? Have some interest in electronics? If you do, you may have at some point looked at like your TV contrast on your screen or your laptop screen. What do you know? Anybody know anything about the TV colors?
Certain screens are more pixelized or show code better resolutions.
Okay, so the size of the pixel affects like the screen, and the actual pixels themselves could vary more from colors based on the brand, for sure. What else?
Is it like a pixel either it's like 3 colors,
Yeah, it's one of 3 colors, isn't it?
and then it's just like a series of them to make a different color?
So if you want to see the color of like somebody's skin and they happen to be like, say, light brown skin color, you don't actually see light brown. You see a combination of these 3 colors, and they are very, 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 very small pixels near each other that when put together give you that color brown. Okay? So if you've ever seen an old TV, before like plasmas and flat screens, have you ever seen the contrast being off on an old TV, like on an actual cathode ray tube?
You mean like
the thick TVs?
After a while, the color goes away?
Yeah,
I
and you
had
start to
that
see
in
like a
Vermont.
shadow.
It's like all yellow now. It's weird.
What you're seeing is these different colors, and usually you'll see like a bit of a shift when the calibration is not correct. Over a long time, these TVs will wear out, and the actual tube that projects the color starts to wear out. And you'll see like a shadow next to people. And that shadow might be one of these three colors. Okay, that has to do with the color alignment not being correct. Your eyes have receptors in them called cones. Those cones see three primary colors. Okay, a lot of people, Anthony, was it you? Say you're colorblind with red and green? Like, not colorblind, but a little, you see shades, right? So, these are the cones in your eyes. It has to do with the cones in your eyes that cause you to be colorblind. It's never going to hurt you, but you just might not see certain colors differently. So your cones in your eyes. Ever seen what a bee sees? A bumblebee? Has anyone ever seen what that looks like before?
I'm not.
They can, but you can see pictures of what bumblebees actually see. They're able to use the eye of a bumblebee or the lenses and the cones and stuff to see what they see. And you know what they see? They see a lot of yellow and blue. Take a look. You could probably even Google it. Maybe we can pull up something if somebody sees one that's good. It's really yellow and blue. I'm not sure what the difference is. I'm sure that the cones only pick up those specific colors maybe, but they don't see, I think, green and red separately. They see yellow and blue. It's like, I think, a navy blue or like a dark, dark blue. Anyhow, the cones in your eyes are what determine the colors that you see. The cones in your eyes. Anybody find an image of that? Is that right?
I'm looking at bees, but it's like more of just bees.
Google what color does a bee see?
Ah, it's easier.
Or what does a bee see?
Dogs see like gray.
Yeah.
Although honeybees have a fairly broad color range, they do not see red and can only differentiate between 6 major categories
Did you do history?
Yeah, you're seeing a lot of yellow that sticks out.
I don't have
There's
the rest of
right there. This one right here is showing the different colors you see, but it's a lot of blue and yellow for bees. Feel free to just Google, look at the images. But
Do we do other animals?
I'm sure other ones have different.
I
Yeah,
also see a color that is purple, a mixture of yellow and ultraviolet.
because they can see that ultraviolet spectrum.
You
We
guys make a
can't.
state of your playpen.
Ah.
Make a little state of your playpen. Oh, what's up, guys? You guys are chill.
You hear that? So bees can't see
That's
red.
their playpen.
Listen, bees can't see red, and on that end is infrared, below red. But they can see like this blue, and they can see UV, ultraviolet. You know that that's why those are the names, by the way? I don't think I went over that yesterday.
No.
Red is here. Sorry, from you guys. Ready? Here's red. Here's violet. Infrared is below red. Ultraviolet is above violet. That's where those rays fall into place. That's the reason of the names. And infrared means below red. Infra. All right, the last thing we're going to talk about, topic of what's called polarization. Now, in the course of this year, we will talk about polarization twice. They are two different things. In chemistry, polarization meant to do with the dipoles, positive and negative ends aligning themselves. We're going to talk about that later in the year. Actually, I may cut that chapter out this year. I'll explain why later. But if we do get to it, we will talk about it again. This type of polarization is not the chemistry polarization, though. Okay? Yeah, that's exactly right. Have you ever bought sunglasses and you're like, why am I going to pay another $100 for polarized light or polarized film? Really, what it is. Why would I pay that? What does the polarization of light do? It reorients the EM wave. So EM waves come in at arbitrary angles, and you can see them in the diagram on the left. The diagram on the left shows that sometimes the magnetic field was vertical, sometimes it was coming out horizontal, but here look at the three waves. They're all rotated so that they're oriented in the same direction. And what that does is it creates light that's then polarized. Polarized light, it has a lot of effects. One of the main effects you'll see, it reduces glare. It changes the actual light you're seeing coming out of it. So for example, light that comes out of your laptop is polarized. Okay? And the idea behind it is that there's like a film that's on top. Has anybody ever seen this before? You could strip this film off of a LCD monitor and you would not see anything. And then when you move the film over, you see stuff that's there. Maybe I could pull up a YouTube video in a second and show you. It's really kind of a cool video with the glasses. You see the guy? He made the glasses, yeah. I actually put that on News for him a while ago. Really cool video about how polarized light works. What's happening again is that it's changing the orientation of the EM wave. again, applications of this are what's important.
Is that anything to do with Polaroid camera? Or is that just a catchy
I
name?
wonder, I don't know. I really don't know that, Frank. Maybe you could look it up.
Look it up.
Polaroid. Polarized. It's possible, it's very possible. So what you're seeing is a lack of glare when you wear these glasses because it changes the orientation of the light that's actually going into your eye. Okay, it reorients it itself. You'll sometimes see this also on like windshields. You ever look at a windshield and when you look at it from a certain angle, you can't really see into the actual car. It's not the tint I'm talking about. It has to do with the light, like a glare on the side of it. So you'll see certain windshields are now polarized. If you wear, you got to try this sometime. If you wear polarized sunglasses and you look at like a cell phone that has a screen protector that polarizes the light, you see some weird things. My old phone, I should have brought it in. Yeah. My old phone, I put like this screen on that actually polarized the light coming out of it. So if I wore my sunglasses in the summer that had a polarized film on them, when you look at it, you would see like rainbow colors on everything. Almost like when you see like a rainbow on the ground, if there's like oil on a slick surface, you see that rainbow of colors, you would see that on your phone. It looked really weird. But anyway, the idea of it is that it's reorienting the light.
So how do the 3D glasses work?
How do 3D glasses work?
Because they do something like that.
My guess, okay, so this is using lenses, something we're not going to talk about, but something I did learn in high school. There's something called virtual images, and virtual images project images a distance from where they are. So for example, if you have a lens that bends light a certain way, the image can be bent so that the image doesn't appear on the surface, but it appears behind the surface. There's, I think I have something up here that I can demo it. There's like these, and all that. And with 3D glasses, I'm assuming that it's creating a virtual image in front of where the actual image should be. So when you see something in 3 dimensions, you see the back of it, but you also see a virtual image in front, which gives it depth. I have something in here, it's actually kind of pulling through with that. Pass it around. Here, and there's one here.
I'm seriously so very jealous. It's like, it's like, there's like,
Yes, to each other.
not that they're gonna talk to you guys. Like, I don't want to.
To who?
Alright, so inside of here is a curved mirror. There's a little toy pig in the inside.
Piggy.
You seen this before?
Nah, I've never
Okay, little toy piggy. All I want you to do is look at this first from the side, okay, without the pig in it. It looks like it's actually closed. Right? You look at it.
Whoa, that was really cool. That was so
Right, there's
cool.
the top right there, isn't there? This is this, there's the top.
Oh, I should
But
watch
what's
this.
kind of weird is this.
Oh, dark magic.
If you look at this from the side, look at it
It's
from the
wizardry.
angle. It looks like there's a top on top of here, doesn't it?
Yeah.
It looks like there's literally a clear top, and then I can
That's something I would love.
drop the pig in,
Piggy.
okay, and look at it from the side from an angle. I forget what the angle should be. Hold on, let me figure this out. I haven't done this.
I
before.
kind of see it.
Yeah,
over
you have
from
to be
over
above.
here.
Yeah. All right.
Yeah,
So-
oh yeah, I see it now.
If you go look at an angle of about 30 degrees, so maybe when I come by you, like half stand up.
This is nuts.
Whoa!
see the big gun
Oh
floating?
my gosh!
Don't look inside of it, but look up here. Literally look where my finger is.
If I see you wear this, I will get violently
You will.
sick. I will get violently sick.
Look
I've
above.
never met any of these kids. I know Ted. I like Ted.
Yeah, it's
so
like
much
floating,
easier.
but it's actually inside. It's above
So funny. Pictures like this.
Yeah, so it's floating on the top.
Oh, yeah.
It's creating a virtual image. It's not really there. Look, when I put my finger here, I'm blocking the light. See how it's getting distorted now? Stand a little bit, okay.
This is probably it all. Physics. Just get violent.
No.
Stupid. Who let you out of the place? Who let you out of the place? Alright. But this is good. You wanna like corner
We
me?
can't put the corner.
Alright.
They're gonna stick to each other
Did I just leave it
anyway,
there? Mess
honestly.
with people?
Xavier?
Just
Let me go to the camera, see if we
I
go
don't
online.
know. Xavier.
Anyhow, so that's it for this section. Here's what you're going to notice. This is a very theoretical section, conceptual, right? No math at all in this section. The previous section, there was pretty much no math at all because it was the same formula as 12.3. In 14.1, we used the formula V equals omega lambda, but we used the speed of light for V. It's the same formula from 12.3. So pretty much all of your math is going to come from 12.3, unless you look at 14.1 as separate math, but it's really the same math as what we did in 12.3. Okay, so chapter 12 is all your math, chapter 12.
For the problem.